So what makes a good pilot network? Well, we need to keep in mind that the design goal of the pilot network is to validate our discoveries from design and emulation, as well as get an idea for the expected behavior of the full-scale network. The pilot network should be both informative of the performance of the hardware, as well as the behavior of the software that's controlling it. So given that we have a limited amount of hardware available to implement the network, we might consider deploying a portion of the full-scale network for the purposes of a pilot network, or we might design a pilot network that's reflective of the least performant aspect of our full-scale network. So some of the biggest influences on network performance include the distances between the network nodes, the number of hops to traverse between network nodes, as well as the hardware components themselves. And so we might try to build a pilot network that reflects the worst cases of these things that we would find in the full-scale network. So for example, I mentioned earlier that quantum data has a notion of quality known as fidelity, and this is one of the most important metrics to evaluate at this stage. And fidelity is one such metric that's heavily influenced by all of these properties of the network. So we'll want to study how fidelity is affected by transmitting quantum data between neighboring nodes, as well as those across the network from one another. And to make sure we can gauge the fidelity in our full-scale network, we'll want the pilot to capture these least performant aspects of the full-scale network. Now, one additional benefit from implementing a portion of your full-scale network as your pilot network is that in doing so, you're actually also making progress towards your full-scale deployment. And so the pilot network will already be reflective of some of that behavior in the full-scale network. However, if this path is taken, then we also need to be aware of whether or not that portion that we want to deploy is actually reflective of these least performant aspects. If it isn't, then there's still a possibility that those worst performing portions of the full-scale network might not satisfy our network requirements. And so we'll want to know how we can use the results we get from our pilot in this case to assess whether or not those portions of the full-scale network will still be sound. So in addition to all of this, the design of the pilot network will also depend on the use cases of the network as well. And to illustrate this, I'd like to go over an example. So suppose that we're building a first generation network that enables quantum secure communications. And let's suppose that we have the following requirements on the full scale network. So first, all of the links in the network are point to point. Next, we require that the network distributes entanglement with a minimum fidelity of 0.9 and at a rate of 10 entanglements per second between any two network nodes. And lastly, we require the ability to run quantum secure communications between any two network nodes in the network. So because the links in our full-scale network are all point-to-point, we'd like to design our pilot network to also use point-to-point links between the nodes. By doing this, our pilot network will account for any loss or noise that will be observed in the full-scale network. Now, if our full-scale network uses the same link infrastructure between all the pairs of nodes, then we can also just focus on benchmarking the worst performing link we anticipate to exist in the full-scale network. If we test this worst performing link, then we can likely assume that all of the other links in the network will perform just as well, if not better. So if we suppose that my full-scale network is composed of these 4 network nodes on the right, then for what I described, maybe my pilot network is just composed of the red and blue nodes at the top left and bottom right corners of my network, because they have the longest link between them. But maybe this kind of pilot network is too simple for testing our software or to inform us about the full-scale network. So for example, the fiber connections between these network nodes might go through an optical cross-connect that needs to be configured. In this case, I'll want to test that my control and orchestration software can properly set up those fiber connections. Or maybe I find out later that there's also a fairness requirement in the network, and nodes should get some proportional share of the available throughput in the network. If I wanted to be able to test the ability of my software to manage this fairness aspect, then I'd likely include additional network nodes in my pilot so that I can test this aspect as well. Now, in summary, the design of our pilot network should be motivated by the requirements we need to validate for the full-scale network, as well as the various software components that will control it. It should permit validation of the hardware in terms of performance and interoperability. It should allow verification of our network protocols. it should permit confirmation of the results obtained through design emulation, and it should be informative of the anticipated performance when the network is scaled up to its full size.